So we do not always need a 95% level of confidence. We can use others. So we do know, we're going to go through this again, that when we were using our Z tables and we were talking about these problems, we were taking out a certain percentage in the middle. So let's say that was 90 in the center. We didn't have a way to figure out what these Z-scores were. So we still can do that, but this chart here is some of our more common confidence levels. We can construct a confidence interval for any level of confidence, anything between 0 and 100, just it can't include those. But generally, we don't go as low as, like getting close to 100. At the very least, a confidence interval of 70 is probably the smallest I've seen. But like I said, there are other levels of confidence, and usually we like to keep them fairly high. So some fairly common ones would be 90%, 95%, which we've already seen, 98%, and 99%. So these would be all those critical values that goes with those confidence levels. So this is my confidence level. This is my critical value. All right. So we're going to do another problem. We're just going to change the level of confidence. So first, let's do this one. A sample has a mean. So we have a point estimate of 7.1 and a standard deviation of sigma divided by the square root of n. So that is my sigma sub x bar. My standard error is going to be 2.3. And we want to construct a 90% confidence level. So I need a z-score for that. Like I said, this chart's kind of a quick go through, so I don't have to constantly look these up. 90 is a common one, so I look here for 90, and I see a z-score of 1.645. So if I want to make my confidence interval, remember it's just going to be x bar plus or minus my z-score times my standard error was one way we talked about it. So that would be 7.1 plus or minus a z-score of 1.645 times a standard error of 2.3. So the margin of error, that is going to be the, sorry, so it's taking a little bit here to boot up, 1.645 times the 2.3. And that is going to be the 3.7835. So that, like I said, that's my margin of error. So then my confidence intervals are going to be 7.1 minus 3.7835, which is going to be 3.3165. And then if I go 7.1 plus 3.7835, that is going to give me 10.8835. Okay, so that was my 90% confidence level. Okay. So my 90% confidence interval. So the reason we have different levels of confidence is it's sort of a little bit of a game. We're trying to make an interval that's not too huge, but we also want it to have a good chance of capturing the true population mean, because that's what we're really aiming for. So it's this combination of, you don't want your interval to be too huge, because then it doesn't really narrow down what your margin or your population mean is, but you don't want to make it so small that you completely miss it either. So sometimes we'll fiddle with these levels of confidence. So just to show you here, let's change this problem. Instead of making this 95, we'll make this 98%. So that means my z-score is now going to be 2.326. So the only thing that's going to really change here is my margin of error, because now I'm going to put my 2.326 in here. So 2.326 times my standard error, 2.3, Well, that's going to give me a much bigger margin of error. So the last one was, what was it, 3.3 approximately? Well, this is a much bigger margin of error, so it gives me a lot more wiggle room. So it expands this interval that I can look at so it can include more possible means, thus the confidence level is going to go up. So if I do that, 98% confidence interval, so I'm just going to use CI. If I take my 7.1, but I subtract my margin of error, that is 1.7502. And then if I add my margin of error, that's going to put me at 12.4498. This is, like I said, there's going to be a little bit of wiggle room of what we can do. We can change that level of confidence. This gives me a smaller range to look for that population mean in, and this one gives me a much bigger one. So I guess something that could be really, really off, because I'm like going between basically 2 and 12. And here I'm looking between a little past 3 and 11. So like I said, it widens that interval. It gives me a bigger area to look at, but then I'm likely to find population means that are really off center. It's gonna be this big range to look in. But we're gonna see that be a problem when we start talking about hypothesis testing as well. So a sample standard deviation of IQ is 15. So we went through this problem once before, and we said because it's not mentioning a sample here, this is population data. So my population standard deviation is 15. It is believed that regular meditation can cause an increase in IQ. We have a sample of 30, so we know N is 30. Because this is a sample of 30, the mean IQ of that sample is 103, so that's my X bar. We want to use a 99% level of confidence. Well, what could that be? The chart says 99% level of confidence. My Z-score, my critical value, is 2.576. So we did this one last time with a 95% level of confidence. So we're going to end up with a bigger interval here. But like I said, this is all we really need. We know what X bar is. We got a point estimate of 103. My critical value is 2.576. My standard deviation is 15, and I'm dividing by the square root of N, which is 30. So my interval, I can just put that whole formula in my calculator. So I can do 103 minus 2.576 times 15 divided by the square root of 30. And this gives me the second. Let's say there's a little mistake here. Times. It's a little off there. 95.95. And then on the other end, we put in addition opposed to subtraction. So 103 plus 2.576 times 15 divided by the square root of 30. We get 110.05. Sorry, I read that wrong first time. So people who meditate, we're saying that we think that their IQ is somewhere between, like all people who meditate, is somewhere between basically 96 and 110. Remember, this is just one sample. There could have been, maybe all the rest of them were like 99%, and this one just happens to be 103. Okay. So we will sometimes use something other than a calculator, or other than a chart that already tells me what all my critical values would be. I have to look them up on my own at some time. So we're going to explain what this alpha means. I'm going to make the slide a little smaller so I have some room here. So we have this Z with this little alpha under it. So this is a Greek letter, it's alpha. It's a Greek A, if you didn't know. So it's lowercase Greek a. So we have something that we're going to call an alpha level. So for us, what alpha is, like I said, it means an alpha level. And for us at this point, it's going to represent something a little bit more in the future. It's how much the probability I can have something wrong is essentially what it is. So in this case, it's the probability that I miss the confident or miss my population mean. Or you could say portion of times we miss it. So every time I make a confidence interval, if I have a 95% level of confidence, then 5% of the time I'm going to completely miss my population mean. Like I said, this is all about proportions. It's not about probabilities. So if I make 100 confidence intervals, 5 of them are going to fail, and that's what alpha is representing, is that 5% that fails. All right. So another way of thinking of level of confidence is sometimes we talk about this area to the right of a z-score. So it's a notation that we use when we are talking about finding these critical values. So when we talk about a critical value, stop here a little bit. We talk about a critical value. What we should be saying is not z, but it's a z alpha, or it's going to be z alpha divided by 2. And where this comes from is the name of critical value. I think I mentioned this before. Is because these areas in the tail are what we call critical regions. So we're not going to really use critical regions so far as as for confidence intervals, more of a hypothesis testing aspect, but there's a lot of crossover here between confidence intervals and hypothesis testing. So these are critical regions. So we usually focus on the right tail. So it's this area that I'm looking at. So if I had a 95% level of confidence, that would mean that what is left over in the tail, or my alpha, is 1 minus that 0.95. Meaning we have 5% that's left over that goes in both those tails, and we've done this before. If I take alpha and I divide it by 2, well, then I'm going to get 0.025, because what's left in each tail, if there's 95 here, would be 2.5% here and 2.5% here. So what we'd end up saying is that this z-score, so if we had a 95% level of confidence, so we say CL, then we write the z-score as z 0.025, because we're signifying what is left in that right tail. And we know this one is 1.196. If we did, say, 90% level of confidence, the same concept here. If there's 90% in the center, that means that alpha would have to be 0.1, because that's what's left over, which means alpha divided by 2 is going to be 0.05, which means that my z-score, my z-score is going to be z 0.05, because it's going to be now 5% left in this tail. And we know that for a 90% confidence level, that z-score is going to be 1.645. Okay. Just explaining what this notation means, because we use this notation sometimes when we're trying to, especially when we start looking at t distributions or student t distributions, we use that notation a lot more. So we want to find the critical value of z alpha divided by 2 for a 92% confidence interval. So we're going to go 2 ways that I can do this. So first thing I need to do is just talk about these areas. So if my confidence level is 92% or 0.92, then alpha is 1 minus 0.92, which is going to be 0.08. So there's 8% left over. So in the tails, alpha divided by 2 is 0.04. So these critical values that I'm looking for here, these z-scores are going to be represented as z, 0.04 to represent what's in this tail, and negative z, 0.04 to represent what's in this tail. And it's these areas that we have are, sorry, so we know these areas here, we just need to find those z-scores. So it tells you right here what the z-score is. I'm going to show you how we're going to find that. So first we're going to do this with the z-tables, and then we're going to do it with the calculator. Okay. So remember what we're looking for. Second, I got stuff here on my screen that's getting in my way. There we go. What we're looking for here is we have this area. We were looking at a 92% level of confidence. So this is 0.92, and we said here was 0.04, and here is 0.04. So we need Z, 0.04. Once we have it, then we know what this one is. So it's this one that we're looking for. But also remember that we have this z-score over here, the negative version, and these are equal. It's just a change in the, it changes from negative to positive. I'm trying to think of the word for that. Sign, the sign changes. So really what it is that if I have a z-score of 0.04 and I need to find it, what I can do is look for this area. And we're going to have to deal with just to change these back into positives. So I'm going to go look for that area, which is going to be right here. Nope, that's one too far. Right here. So that is the closest I'm going to get to 0.04. So remember, all I need is I just need to go backwards and get the z-score that goes with that. So here it's telling me that the z-score is negative 1.75. So what it really is that what we found was this area that's to the left. So we actually found the negative z-score. So that's what we're finding first, is that negative z-score here. So this is negative 1.75. So if I want the other one, then all I have to do is I just have to change this negative into a positive. Same thing's going to happen with our calculator because we just calculate everything to the left. So we're just using that left tail and we're just mirroring it to the other side because we know, like I said, that the negative z-score for 0.04 in that tail and the z-score for 0.04 in the other tail, they are equal to each other. It's just that they have a change in sign. So they're equal in magnitude, but different in sign. Okay. So there's going to be a slight change of how we use the calculator here. So in this case, when we're dealing with these, looking for critical values, because this is supposed to be just a standard normal distribution, what we're going to say is that my mean is going to stay 0 and that my standard deviation is going to be 1. So we're not going to do like we did before because we're not looking for an X value. We're looking for that, like, yeah, we're just looking for that z-score, and then we're going to keep these at 0 and 1. So we're going to do what we did before, like if we wanted a z-score and we were trying to go backwards, is we're going to go to second, and we're going to go to vars, because that brings up my distributions. And we need number 3. So we're inverting the normal curve. Your area in this tail is 0.04. So like I said, I'm going to leave it as a left tail for now because a lot of your calculators can't change which tail it is. So we're going to leave it to the left so everybody can see what we would do. Unless you change these, they will always default to 0 and 1. But like I said, we're going to say that the mean is 0, the standard deviation is 1 because we're looking at a standard normal curve. And we're going to get my critical value. Remember, this is giving you the negative z-score because it's always looking to the tail to the left. So it tells me the negative is going to be negative 1.75. And we could round that to 1, but like I said, we only round 2 decimal places for z-scores. So if I want to make it the other z-score, the positive, well, then I just change the value to a positive. So that is all we need to do to figure out what that z-score is either we just look for that tail, so we just keep using the left tail, and then we just figure out what the z-score would be for that left tail, and then we just change it from a negative to a positive, and that gives me my critical value. So our answer here is that I'm going to have a critical value of z subscript 0.04, and that is going to equal 1.75. So fortunately, we already know that's the part of the answer to this one, so we can just go work our way through it. So just as another example, body temperatures have a standard deviation of 0.7 degrees Fahrenheit. Once again, I did not mention anything about it being from a sample. I said body temperatures are blah, blah, blah. This means this is population data. So I don't mention anything about sample. We assume it's population data. So that means sigma is 0.7. We have a group of 50 individuals. So my sample size is 50 with influenza A, and they have a mean body temperature. So this is a sample. We have a sample mean, so an X bar of 100.8 degrees Fahrenheit. We're going to use a 92% level of confidence. So we just found out, well, if I do a 92% level of confidence, that means there's 4% left in the tail. The z-score for 4% left in the tail is 1.75. Like I said, we just found that in the last problem. So like I said, all that was required here is this, we just had to do that little extra work of just figuring out what's in the tail and then finding the z-score that goes with it. So my margin of error is X bar plus or minus, we're going to say Z alpha divided by 2 now, instead of just saying a z-score because we're signifying this critical value. And then we're going to have sigma divided by the square root of n. So to fill this in, oh, we got 101 degrees plus or minus my critical value, which is 1.75. We have a standard deviation of 0.7, and we're dividing by the square root of the sample size, which happens to be 50. So we'll find my margin of error first here. Like I said, sometimes we write confidence interval with just the point estimate and margin of error. And then sometimes we write it as a whole interval. So we'll kind of go between both of them so we can see them. So usually temperatures, anytime I've done confidence intervals or anything like that, they don't have a lot of wiggle room because they have such small standard deviations. So this rounds out to, if I go out 2 decimal places, to 0.17. So this is my confidence interval for a 92% level of confidence. So 92% confidence interval. That's going to be 100.8 plus or minus 0.17. Or if you'd like to actually see an interval, I didn't go in right the first time. That means that the temperatures are going to be, for 92% level confidence, vary between 100.63 mu, and then the other side would be 100.97. So, like I said, out of this group of people with influenza, we had a temperature of 100.8. If we build a confidence interval around this, we're going to find that what we think the mean temperature of influenza. This is the mean temp for people with influenza A. So what we expect, according to this, that if we find people who are a group of people who have influenza A, we find a mean of everybody who's ever had influenza A, the mean of their temperatures is somewhere between 100.63 and 100.97. I think when I looked it up, it's actually 100.3 is what I had seen. So like I said, sometimes we'll just miss it, but that's what we're doing. Is we're just making our best guess. 100.3 is definitely like the point when you have a fever that's bad. It's a real fever. Anything below that's usually considered low grade fever, and sometimes they're kind of ignored. When you get to that point, that's when they go, yeah, you definitely have a fever. All right, so these are just some of the remaining tidbits to go over. So when you are doing a confidence interval, remember that you are dealing with a distribution of means. So the distribution of means had some criteria before we can even actually look at them. So like I said, the assumption for constructing a confidence interval for population mean when the population standard deviation is known is that we have a simple random sample. So that's always a criteria. We want to make sure that every sample I collect has the same probability of happening. If it doesn't, my probabilities don't make sense. And the other part, and this comes from distribution of sample means and central limit theorem, the distribution of X bars is normal if the sample size is larger than 30 or the parent population, the original population, is approximately normal. So we've been kind of ignoring these assumptions. For one thing, the simply random sample, we kind of assume that's what's going on. We really can't prove that so much when we're given just raw data. However, the second part we can look at. So when we did the IQ problem, we had a sample of at least 30. So it didn't quite fit that first probability because it wasn't larger than 30. However, we know that the IQ is normally distributed, so we were okay there. When we were looking at body temperature, we don't know if body temperature is normally distributed because we haven't really I don't think we've really discussed that one before, but my sample size was over 50, so everything I did is okay. But technically, before you even do a confidence interval, you should actually check to make sure your distribution of sample means is normal. So normal is what we should be doing. We've been just kind of skipping around that because we've just been trying to get the idea of a confidence interval. So just as an example, the lifetime of a certain battery is known to be normally distributed with a standard deviation of 20 hours, and a sample of 50 batteries has a mean lifetime of 120.1 hours. So we need to first verify that everything is satisfied. Well, one thing, I can't really guarantee how the batteries are sampled. We assume they're simply random, but we have two things here. The original population, just a second, maybe that wasn't in there. I got something that's in my way, so I can't read. Yeah, so your population was normally distributed. So that satisfies central limit theorem. Also, the sample size is over 30, so that satisfies central limit theorem. So verify assumptions are satisfied. Yes, they are satisfied. Then we want to construct a 95% confidence interval for the mean lifetime of the battery. So if I'm doing a 95% confidence interval, there's 5% left over for my alpha. If I divide it by 2, I get 2.5. So I'm looking at Z 0.025. And we've done this one a couple times. We know that's going to be equal to 1.96. Okay, so we're going to construct that confidence interval. So we were told that The batteries are normally distributed with a standard deviation. So sigma is 200. We have a sample size of 50 batteries. And the mean for that sample was a battery life of 120.1. And our z-score, we know from 95%, that's one of our common ones, is 1.96. So my 95% confidence interval, I'm going to put CI, is going to be 120.1 plus or minus 1.96, because that's my z-score. And then my standard deviation is 20, and we're dividing by the square root of the sample size, which happens to be 50. So if I get that margin of error, 1.96 times 20 divided by the square root of 50, that means I'm going to have 120.1 plus or minus 5.54. We'll round to there. So that's my confidence interval. That's one way to write it. Or I take my 120.1 and I subtract my margin of error, which means I'm going to have a range of 114.56. And then that's less than my population mean, or I assume. And the other side of that population mean, the highest we expect it to go is 125.64. So those are my confidence intervals. Is it likely that a population mean, the population mean is greater than 130? So is it likely? So remember, when you are constructing this, I am saying that I think that my mean is somewhere between, I'm not going to write all the numbers in here, so we're going to just shorthand that to 114 to 125. And we said in this range is a 95% chance that mu is in here. So what's the probability of it being over here? So 130 is over here. So remember, the area in this tail is 2.5%. So there is a less than 2.5% chance that my mean would be greater than 130, because 130 is over here. So this barrier starts at 120, 130 is here. We know that there's going to be less of a chance for it to be greater than 130 than it is to be greater than 125. So the probability, oops, I forgot my P. Like I said, basically it's this. The probability that my mean would actually be greater than 125 is at 2.5%. So if I went even any higher than that, there's even less of a chance. So there's less than a 2.5% chance that my mean is going to be greater than 130. This is below. So remember, things start being unusual or unexpected when it had less than a 5% chance of happening. So anything below 5% is not likely to occur. So this is not likely to occur. So C is kind of just bringing together a little bit of everything we learned. But this idea here that, well, what is the probability, or is it likely to have a battery, or all my batteries have a mean life of 130 or more? Well, this gets us into a little bit of what hypothesis testing is, as we're trying to figure out, is this a likely event? And if it's not a likely event, then we'd say, no, it's not like this isn't going to happen. So this is like a soft hypothesis test that we did here. Is it likely that your population mean for your battery life that to be over 130? Not really likely, because like I said, we know that in this tail is 2.5%, and that is just for looking at something from 125 and greater. which is already rare. So to have 130 or greater, that's even less rare. And as long as it's under 5%, like I said, that's our threshold for now. We can change that, but as long as it's less than 5%, it's going to be weird. Basically, 130 is in my weird area.